Good afternoon. Welcome to session 3B. Well, this is a very special session of FM. It's the first time that we have what we call the journal first track presentations. As this is new to FM, I will give some motivation for that. I'm sure some of you know this from other conference. So the idea is that some papers are published directly in journals, the original contribution, without previous versions in conferences. So, of course, this can happen, it's a normal thing, but it's a pity that sometimes you don't have the social aspect of having live discussions about these papers, because they are published in journals, and then you don't have an audience like this to discuss the contributions. So, motivated by this idea, we start in FM in this edition. And then we have a look at some recent papers published in two journals of our area, the formal aspects of computer, aspects of computing, and formal methods in system design. And then we had a look at several papers there, and then we selected 3 papers for being presented in FM. So the committee was led by me, and then with the help of Cliff Jones and Manfred Broy. And then we select these papers. So in this session, we have just one paper that I will introduce our speaker in a moment. And then the other 2 papers will be presented on Friday. One will be presented at 2 o'clock, and the other one is going to be presented at 4 o'clock on Friday. So you should not miss this session. So for this first session, I would like to welcome Eunsuk Kang from Carnegie University, and he's going to talk to us about Alloy Star. Okay, welcome.
Thank you. Can you hear me? Yes? Okay, great. Thank you for the introduction. This is joint work with Aleksandar Milicevic, who's at Microsoft now, Joseph Neer at University of Vermont, and Daniel Jackson at MIT. What is Alloy Star? So Alloy Star is an extension of another tool called the Alloy Analyzer, which itself is a constraint solver for first-order relational logic. Okay? So Alloy Star or Alloy Analyzer has been used for different kinds of applications, ranging from performing bounded verification of software, analyzing safety properties of traces, synthesizing configurations, as well as just finding an instance to a property. Now, Alloy does have limitations, and one of the limitations that it has is that the analyzer can't really be used to analyze models that have higher order constraints in them. Okay, and so this places certain kind of restrictions on what Alloy can be used to do. For example, Alloy Analyzer cannot be used to synthesize programs. It can't really be used to generate an instance that has some notion of maximality. So basically, though, this work is about trying to address these particular limitations of the Alloy Analyzer. So maybe I can give you an example to demonstrate the problem here. So suppose that you want to use Alloy to find the graph with some clique in it. Okay, so clique is basically some subset of the nodes in the graph where every pair of nodes in the subset is connected by an edge. Okay, so very quick introduction to Alloy. So in Alloy, you can use what is called a sig, short for signature, to define or declare a set of objects. So here, when I say sig node, I'm saying there is some set of objects that represent nodes, and then each node has some key value that's assigned to it. And then I can write a constraint that says, find me something called edges, which is a relation from node to node, and also find me some set of nodes called clique, such that some predicate named clique is evaluated as true over the edges and the clique, the set clique. And then we can define the predicate clique as basically as a constraint that describes the definition of a clique, right? So for every disjoint pair of nodes in the set, there must be an edge from N1 to N2, from N1 to N2, okay? So Now what we can do, we can type in these constraints, and the allo is going to basically try to, when you run this command here, allo is going to try to find a satisfying instance to this constraint inside the run command. Okay? So you can do this. So what allo is going to do is going to do some thinking. It's going to basically translate these constraints into a CNF to be solved by an off-the-shelf SAS solver, and it's going to return some solutions. So in this case, it could return a graph where it could say, okay, these two nodes here, N1 and N3, is a clique. It's one of the cliques in the graph, right? Because every pair of nodes, I guess N1 and N3 are connected by an edge, okay? So this is something that Allo can already do. Now let's look at a different problem. So suppose you want to find, again, a graph and a clique, but we want to find a clique that's maximal, meaning that there should be no other clique that has more nodes than the one we found, okay? So how do we do this? So to find such a clique, maximal clique, we can write a constraint like this. We can define a predicate that says max clique, again, defined over some as relation and some set of nodes that's in the clique. And it says that that clique set clique is a clique, as defined by the predicate clique. And for every other subset of the graph, that subset better not be a clique and also has more nodes than the set clique that we already found. Okay? So this hash here is a cardinality notation that gives you the set size of the set. Okay? And then you can, again, say, okay, find me some graph such that there is some clique that is a maximal clique. Okay? Now, the problem is that now this is a different kind of problem, right? In particular, now we have a quantifier here that's higher order, right? We're quantifying over sets of objects, right? And what happens in Allo is that right now, if you try to run this command to find a maximal clique, it will say, I can't do it because it's a higher order constraint and I can't analyze it. Okay? So how do we, so basically, again, going back to the whole point of this work, so we want to basically extend our analyzer to be able to analyze models that have higher order constraints like this one. And just a little bit of digression, it turns out that the problem of finding a maximal clique is fairly similar to another kind of problem, which is program synthesis. So in program synthesis, what you want to do is you want to find some program such that for all possible evaluation or all possible environment or all possible assignments of values to input variables, the program must satisfy some spec. Okay? Now, if you look at the problem of finding a maximal clique, it has a fairly similar structure, right? So you say, I want to find some set of nodes that's a clique, such that there should, just here, this is the spec. So for every other subset of nodes, that better not be a bigger clique, right? So in other words, they sort of share this sort of same exists for all quantifier pattern, right? And then the for all quantifier is a higher order. Okay? So basically, this is where we sort of got inspiration for Alloy Star. The key idea behind Alloy Star is based on this idea of, well, the approaches to solving the problem of program synthesis. And in particular, the one that we took inspiration from is called Circus, or short for counterexample guided inductive synthesis, which is one of the most popular and well-known paradigms for solving synthesis problems. So let's see how this works. Suppose, again, I state the problem of synthesizing a program as find me some program such that for all possible environments, the program must satisfy the spec. Okay? So the way the Circus works, the first step, what we're going to do is we're going to try to, instead of trying to find a program that satisfies the spec for all possible environments, we're just going to find a program that satisfies the spec for one environment. Okay? So we basically transform this original problem into a slightly different problem where this second quantifier, the for all quantifier, is turned into existential quantifier. Okay? So when you do this, suppose you use a constraint solver or verifier or whatever to do this, you're going to basically find some program that works for that one particular environment. Okay. And then what we're going to do next is we're going to take that candidate program, right? And then we're going to just try to check it and see whether it's actually a correct program with respect to the spec, right? So we're going to just say, check for all environments, does the program satisfy the spec? Okay? So if the verifier says yes, that means we're done. This program is indeed the correct program. If not, then some verifiers, including Alloy, will give us a count example that demonstrates how this program, or basically demonstrates or represents the environment under which the program violates the spec. Okay? So what we're going to do next is we're going to then take that counterexample. Okay, so counterexample, we're going to, in this case is this particular environment, and then we're going to solve the problem of finding another candidate solution, right? Except this time, we're going to take that counterexample environment and we're going to append that to the problem that we solved in step 1, right? So we're going to say that find me a program such that there is an environment that the program satisfies the spec under the environment, and also program must also satisfy the counterexample environment they found in the previous step. Okay? So if this returns unset, meaning that if this is not satisfiable, if there is no such program, that means there is no solution to this problem. But if there is, then basically we can go back and check this new candidate we find and repeat this process as much as needed until we find a program that satisfies the spec for all possible environments. Okay, so that's the introduction to Circus. So basically what we did was, the idea behind Aleksandar is that we're going to apply Circus to solve not only higher order constraints that is in the form of exists for all, but we're going to try to solve, basically try to use this approach to analyze any arbitrary alloy model with any arbitrary patterns of higher order quantifiers. Okay? So again, the goal is to be able to extend the notion of Circus and to be able to solve any arbitrary higher order quantifiers or any models with arbitrary higher order quantifiers. And then another goal here is that we don't want to require the user of the tool to provide some kind of domain knowledge, right? So we want this tool to be fairly generic. And unlike certain program synthesizers where the user has to provide a domain-specific input, we want this tool to remain domain independent, like the way Alloy is. And then there's, I'm going to talk a little bit about later a couple of features that are really important to make this work as part of Alloy. And because of this generality, I think the nice thing about being general is that the Alloy star, like Alloy, can be used in different number of applications, including synthesizing programs, synthesizing security policies, solving graph problems that are higher order, and also solving verification problems that require higher order spec. So here's an example of another kind of problem that Alloy star can be used to solve. So to demonstrate the idea that basically Alloy star can solve quantifier patterns beyond just exist for all. So this problem here is again finding out some maximal clique, except we want to find a maximal clique that also is maximal in terms of the sum of the values that are assigned to the nodes in the graph or in the clique, right? So you can say again, suppose you define some function that takes a clique or some set of nodes and returns the sum of all the values in the nodes. And then we can say, then we can ask Alloy, find the maximal clique such that for every other, again, clique, if that clique is maximal clique, then the sum of the values in that clique better not be larger than the one that we already found. Okay? So this is an example of a higher order problem where it has a sort of nesting of higher order quantifiers, because you have the max clique, which is itself has a higher order quantifier, and then again inside this quantifier we also have another max clique. Okay? All right. So I'm just going to briefly sketch out the high level idea behind Alloy star. So the way this works is again, Circus is defined for only a single pattern or style of quantifier pattern, which is exists for all. So what we're going to do is we're going to try to generalize this to any arbitrary formulas in Alloy. So the first step, what we're going to do is we're going to take the original constraint, and then we're going to transform this into a negation normal form. Okay, and we're going to apply some standard squamization to eliminate existential quantifiers. And then what we're going to do is we're going to decompose the constraint into 3 different types of sub-constraints or sub-formulas, where that constraint or the sub-formula can either be some kind of first-order logic formula. It can be a disjunction of 2 formulas. That's either, again, higher order or first order. And then lastly, we're going to, the third kind of sub-constraints or sub-formulas we're going to get is going to be in the style of exists for all. Okay? And then what we're going to do is just going to basically apply the techniques that we have to solve those problems independently. So for first order logic formulas, we can just use the standard technique that's used by Alloy to find the satisfying instance, which is in this case, the way Alloy works, it translates the problem into intermediate representation in a tool called COD, which is a first order relational solver. And then for the sub-constraints that are in the style of, in the pattern of exists for all, we can apply Circus. Okay, so that's the sort of high-level idea behind how Alloy star works. And if you're interested in the actual semantics of the translation as well as the solving, the evaluation, then you can look into the paper. All right. So I just want to maybe briefly describe one of the details in the implementation. So I think maybe what's most interesting, is so this step here, when we find the candidate solution, and then when we check the candidate solution against, let's say, all possible environments, all possible executions, and then if we get a counterexample, what we have to do is we have to basically add that counterexample back to the original constraint that we solved, right? And then as we search more and more candidate solutions, this constraint that we're solving is going to become larger and larger because we're adding, every time we're adding a new environment or a new counterexample to the formula, right? So one of the key ideas behind the implementation of Alloy star is that to make this process more efficient, we're going to basically use solvers that provide incremental solving capacity, meaning that when you add, you have a problem that's already solved, and then if you add a new constraint, if you use incremental solver, you don't have to resolve everything. You don't have to restart the entire solving process. And in fact, the solver can actually reuse the clauses they learned from the previous steps to solve the new problem with additional constraints. Okay? So this is one of the key ideas that we have in this behind the Alloy star. And so we also implemented a bunch of optimizations to, again, try to make Alloy star more efficient. Because in general, solving higher order constraints tend to be much more difficult process or much more less tractable compared to solving first order constraints. So what we found in the initial development of Alloy star was that if you have, again, a problem like this, suppose that, so what we found is that often when people want to solve synthesis problems, they have a sort of pattern of specifications like this. So they say, okay, I want to synthesize some program such that for all evaluation of the variables or expressions in the program, if the evaluation adheres to some semantics of, let's say, the programming language that the program is defined on, then it must satisfy the spec, okay? Now, what we found was that if you have this kind of implication here, what we end up is that often Alloy star will find a counterexample where the evaluation or the environment, the counterexample environment, does not satisfy the semantics predicate. And therefore, it sort of trivially satisfies the spec, right? So what we found was that this kind of candidate solutions are not very helpful for pruning the search space while we're searching for a solution to a higher order constraint. So what we did was we implemented an optimization that basically allow the user to specify, okay, I have this predicate that I know must hold over the candidate solutions that we find. And then whenever we generate a counterexample, that environment will satisfy that semantic predicate. And this is really helpful for reducing the number of steps, or number of iterations that the solver goes through to find the solution to a higher order problem. All right, so let's talk a little bit about evaluation of the tool. So does this actually work? So what we wanted to do, we wanted to sort of do two things. We wanted to, or actually three things. We wanted to see whether Alloy Star scales on problems that are sort of graph problems that are beyond the sort of toy size problem. So when you look at, let's say, an Alloy textbook or papers, typically you have to provide a scope on the size of the universe so they can actually finitize the problem. And typically the scope is things like 5 or 6. And some people sort of perceive that as being too small, and maybe the problem you're solving in Alloy is a toy problem. So we wanted to demonstrate that basically Alloy Star can be used to solve problems that are much larger in scale compared to typical scope of 4 or 5. We also wanted to demonstrate that Alloy Star could be used for solving one sort of big domain of synthesis or problems that involve higher order constraints, which is program synthesis. So we wanted to see whether we can we express these kind of problems, right? So what we did was we looked at what is called the Circus benchmark. So Circus stands for syntax-guided synthesis. Yes, thank you. Which is basically a benchmark of problems that are used to evaluate different program synthesizers. And then we just wanted to compare whether Alloy Star scales to other tools that are competing in these benchmarks. So, okay, so here's just one example of, so we applied Alloy Star to a bunch of graph problems, and then we see that actually, so this is the size of the node, so this is nodes being the size of the graph, right? And then we see that actually for most of the problems, Alloy Star actually scales fairly well, right? So you can actually solve, you can find graphs of size beyond, let's say, 25 within a reasonable amount of time, right? In terms of the comparison to the Circus competition or benchmarks, so we're actually able to express a lot of the problems that are part of the benchmark. And the ones that we skipped are sort of things, the reasons that are sort of due to the technical reasons that are not really, I think, fundamental to Alloy Star. For example, there are certain kind of problems that require 64-bit vectors, which is not supported by the underlying solver behind Alloy, which is COD. Yep. And then what we found was that Alloy was actually able to solve all of the problems in different categories of the benchmarks. And actually, this, in terms of scalability, Alloy Star was actually also comparable to these other tools that are evaluated on the same benchmark. Okay? So for example, here's a graph showing the comparison of Alloy Star to other program synthesizers that were evaluated on the Circus benchmark. And then we found that, Alloy Star is not always fast, right? Sometimes it can be slower than compared to other tools, but in many cases it does very well, and it is comparable in terms of the performance compared to these synthesizers that are optimized for these kind of problems, right? So again, to emphasize, the Alloy Star is intended to be a general purpose language and a tool, right? So the fact that it can perform fairly well, even with the additional generality, I think is a really nice property of Alloy Star. And then just to show you the optimizations that we implemented actually was fairly important for optimizing, ignore that notification on the right, for basically making the solving process much more efficient than it will be without the optimizations. All right, so anyways, to conclude, so hopefully you got some understanding of what Alloy Star is and how it works. So basically, Alloy Star is a general purpose constraint solver for higher order logics, right? And I think, it's in terms of efficiency, is comparable to other program synthesizers, but also is more, I think, general, right? You can use, because the Alloy's logic is fairly general logic, you can also express different kind of problems that maybe will be hard to express in a more specialized synthesizers, right? And actually, many years ago, Daniel Jackson, he tried to actually implement a solution to solving higher order problems, higher order quantifiers. And the way he did it was basically essentially grounding out the quantifier, even if it's higher order, and try to translate it into a CNF. And it turned out that that approach just didn't work at all, right? But this new approach of sort of applying Circus kind of sort of incremental iterative approach to synthesis was really helpful to making Alostar usable and practical. And I think, hopefully what we're hoping to see is that people will use Alostar, right? People already use Alloy, or people already haven't used Alloy because of limitations of Alloy. Hopefully they'll get a chance to use Alostar, and maybe there will be new applications that we haven't thought of that they will emerge from the use of Alostar. Okay? So please try out the tool. You can download the tool for free from this link here, and I'll take any questions. Thank you.
Okay, good afternoon. I thought there was going to be, technical sessions and some stage a two-paper session, so it's a bit of a surprise to discover that the two have been combined here. So I'm trying to keep to the spirit of the program. I'm going to first give a talk generally about the problem of translating Circus into CSP for model checking, and then I'll pause and take questions. And then what I'll do is the tool talk and demo the tool as far as I can. I'll explain when I get there. So this is work. This is really work done by Artur Gomes. He was a PhD student with me under the Brazilian Science Without Borders funding. He stayed with me for 4 years. He's gone back to his place of employment, University Federal de Mato Grosso. Unfortunately, he was not able to travel and make it, so I'm kind of presenting this work. But these are kind of his slides and his work. So I think the key thing here is that so Circus is kind of an extension. He says an extension of Z or an extension of CSP. It's a fusion of the two. And it's based around taking the notion of the paragraphs of Z and adding new paragraph forms that define Circus channels, processes, and actions. And the channels correspond to CSP events. And the main distinction or the main change is that in Circus, you've got CSP processes with the ability to read and write shared variables. And these are usually defined through a Z schema. So the Z schemas are defining before and after state, and ultimately how those variables get updated. Right? I'm not going to go into there are very subtle semantic distinctions that emerge from that, and I can answer those in questions, but I'm not kind of going to cover them. And so the current state of play is that if you want to model, if you've got a Circus model and you want to model check it, the most effective route is to translate it into machine-readable CSP and then use FDR. And that's really the focus of this talk. And an example was early work that Artur did during his PhD, where he basically put in a Circus model for the hemodialysis case study for ABZ, and that was accepted, and that was all very nice. But there it was a matter of having a model built in Circus of the hemodialysis and then translating by hand. And then was able to do the usual kind of checks that you can do with FDR. All of FDR is available. And the problem, of course, is that as these models get larger and more complicated, translation by hand is very error-prone. You spend a lot of time fixing it up. Because basically you've got to work around the fact that CSP doesn't have updatable variables. So you have to somehow turn variables into parameters of a CSP process in some way, right? And so what Artur focused on was a particular deliverable. I think some of the people involved are in the audience here. A Compass deliverable, D24.1 from the Compass project. And that was in a more general setting with, I think, the language CML. I think Jim has memories of this area. So there's a lot of work there on using Circus in various settings. And in part of that technical report, there's a description of a translation scheme to get from a Circus model into machine-readable CSP. And basically the idea behind the I think it's actually on the next slide, yeah. So the idea basically was that you had basically two functions. There was a kind of a big omega and a big upsilon. And the omega functions were involved with changing Circus into basically CSP. And then the upsilon function was really just transliterating the CSP here into machine-readable CSP. So the interesting work is really in the omega functions. So the first step taken was simply to create a memory object. So all the variables in the Circus, in all the Z schemas in Circus would be put into a memory object, and that would be running in parallel with a process here. And the idea basically is that now that this process, instead of directly modifying variables, would use get and set messages to talk to the memory. So we're going to, is a classic way of using CSP to model a mutable state. You have a CSP process with a state, and you have a message, you can set the state, and you can get the state. So it's the basic idea. And then there are a series of refinement transformations are then applied to this process model so that it plays nice. So it's really, this is using the Circus refinement techniques to get across through the translations. In a handmade translation, you end up using these gets and sets. As I was saying, reading, updating the values of the sets. You have to create 2 channels for each state variable. I think I've pretty much said this. The main issue is when you're doing this manually. So the technical report described this translation, but there was no mechanizing for it. It just said, follow this schema. So it was a good scheme, follow it. But it left the human doing a lot of bookkeeping, and it was quite easy to be error-prone. And it looked like a good candidate for mechanization. So this is basically the Circus to CSP tool. So it's a tool for automatically model checking Circus. That's the plan. So automatic translation from Circus to CSPM. It's based on Oliveira's translation from the Compass project. And basically, it's a repeated application of Circus refinement laws, almost all of which are, in fact, equivalences. So you're just churning and doing lots of simple steps. And these all come from Marcel Oliveira's PhD thesis. And there is actually various bits of tool support out there for doing this. So basically, these rules are used to refine a state-rich Circus into a much more stateless or state-weak typical CSP processes, all the state being pushed into the memory object. And then you could map that to CSPM. Now, so that was the idea. So it then becomes an interesting story because what happens is you come up with a scheme for doing something, a translation scheme. And when you do it by hand, enacting a process by hand, you find ambiguities and stuff, you make decisions, you resolve it. But once you start to mechanize things, you start to hit hard limits. You have to nail various things down. And so an initial when we originally built the tool, and he took examples from, there were a number of worked examples in the Compass deliverable. Everything worked fine. And in particular, won't go into the technical details, but there was a notion of you would have various integers, and sometimes parts of your model you'd only use a sub-range of those integers. And since in model checking you're always trying to keep the state space small, if a part of your model that you want to check for, say, deadlock only requires integers from 0 to 5 rather than 0 to 10, you define a subtype, a range type of 0 to 5, and you can make these, in FDR allows you to declare these as subtypes of a larger type. So there's a subtyping mechanism, and they make extensive use of that in the translation. The problem with the subtyping mechanism And they translated using various. There's a functional language embedded in CSPM. They use that. The problem was, it required all the originally they had a master subtype from which all the types were derived, and that was fine when what you were using, say, was int. But the problem that we ran into was that the hemodialysis models that had some enumerated types. It was a mix of types. Now, we could have recoded them all as ints, but Arthur said, no, you shouldn't have to do that. You should just be able to handle the types that somebody might put in for readability into their model. So that basically involved breaking down. So the original model had a large bindings, which is the mapping from variables to their types. So there's a kind of meta information. This was the parameter to the memory model. And basically what we had to do was for every distinct set of families of types and subtypes, to split them up. So we had to split the bindings down, right? So there was the memory model was monolithic and then was broken down into subcomponents. And so now we had a new memory action supporting multiple parameters. So this was just us being pragmatic, supporting a wider range of Circus models. And this is just a fragment of the Circus. So the original memory model just had one of these bindings, which is, as I say, a mapping from variable names to values. And then you just had one get and set message for each variable name. Now what we have is a number of bindings for each of the supertypes, and everything is getting the memory model is getting a bit more complicated. But this is all generated automatically, so it doesn't matter so much. So the new memory, it uses a smaller set of smaller bindings. And we did notice that things seemed to run faster when we did this, when we worked the old examples. But we also found that we really, even if variables only took 2 values, right, there was actually an upper limit of the number of variables. The translator thing, FDR, would choke if you had more than 10 variables, right? And the hemodialysis study had a lot more than 10 variables. But we'd also noticed that because we started breaking down the memory space, some things seemed to go faster. So what the kind of the research activity, Artur started exploring more and more splitting of the state space. And trying different refinement laws, different ways of encoding essentially the same thing. And a whole sequence of translation steps that were added in, all justified by refinement laws. And basically he worked incrementally improving the performance of the resulting models. And the memory model eventually became completely split apart into basically down to the point where you had a memory model per variable. And the question is, why didn't we do that at the beginning? Well, the original Compass translation had a monolithic memory model, and we started by being faithful. Also, it's much easier to show the refinement when you introduce the monolithic memory model. It's a simple refinement step, whereas in fact there's a lot more work to get down to breaking everything down. But it had a distinct improvement on the performance, and so it's quite a while since I looked at a lot of this code. So you're basically breaking it down into like a memory cell for like each variable. So and you're doing a kind of subsetting on the bindings. And so the memory model is very, you've now got lots of these processes all assembled together. But to read the memory model, it now looks very complicated, but the actual model checking performance is much better. So this is kind of the final memory model. And And in fact, there's probably one last optimization set where we can simplify the actual event structure of the mget and mset, the memory set and get channels. So it reduced the state space exploration, and this is something I'm not an expert in model checker building, but there was quite dramatic improvements. There are tables and figures in the paper, but we were able to take quite large state spaces and successfully model check them. And in some cases, the model checking time dropped from several minutes to milliseconds. We got dramatic improvements with the memory model. And we used FDR. We took out, because the memory models is fairly standard, we actually took the old memory model, which is in CSPM, and the new distributed memory model, and we used FDR mutual refinement to check that they were actually the same behavior, and they did have the same behavior. So we actually able to use FDR to do this kind of double check of what we've done. And the result was then that we were able to model check the hemodialysis case study, choosing sensible values, but reasonable values for all the various variables. So that worked. Okay, so so the distributed memory model, that's just showing the actual memory process with bindings, which are pretty much and then it's broken down. Actually, I think this is so he's been producing this slide. I think this is just showing the role of the translating a memory component. I'm not quite sure what that slide is about. So this is always the problem presenting someone else's slides. Okay, so there's one interesting bit here, and this is the potential controversial step. We got a major performance improvement by doing, so I said all the translations, we're using refinement laws, but in fact almost every refinement step was an equivalence, right? There's no proper refinement, except one case. And so there's a point in the model where we had something of the form for some binding element, some indexing set, B in an indexing set, you've got a non-deterministic choice over processes parameterized in some way by that B, right? And this was the top level of the Circus model, which means that given this, FDR has no choice but to check every single one of those values, members of I, right? So even if I is quite small, maybe it's only 10 elements, you're going to have an initial state which you have a 10-way branch, and off you go, right? Now, this is an extreme, but it has the advantage, this is a kind of a closed process, no top-level parameters, off the model checker goes. But decided to say, well, what if we just picked one of those bindings, P, and we'll model check that. And now you have to supply a concrete value for the binding. So this is a refinement. And this is very definitely a proper refinement. In fact, it's about as maximal as it's possible to get. Instead of trying all possible starting values for B, we're going to pick one. Now, that's very unsound, because anything you can prove in this model will only apply to that starting state, and there could be all sorts of terrible things that happen when you start elsewhere. Right. So this is quite a drastic step, and there was a very big performance improvement, very big. So the question is, what do you do now? We've got an unsound step, but the model checker is really good. And then this comes to something, I don't think I invented this word, but this is something in applying formal methods in the real world called pragmatics, right? So the people who are most likely to use, certainly from my reading of literature, most likely to use Circus are people working in safety-critical areas, right? So somebody who's just then making a new web server should probably use Circus. It's very good, but probably won't. But in the safety-critical sector, it's generally, in fact, in some cases it's mandated that you initialize all your variables before you do anything. Your program, your safety-critical program, wherever it is, first thing it will do is initialize all its variables, right? This would be part of the code review, so on and so forth. So the point we were making was that And also, if you look in the literature at circus models in the literature, they're always described as, a bunch of definitions, and there's always an init process and then the main process. This is a standard, it's an idiom. I don't think it's required by the syntax, but it's a standard idiom. It's a very good disciplined idiom. And it has the simple consequence that non-deterministic choice means you've got all of these start points. By the time you've run the init, you're down to one state, right? And in fact, as long as there are no events occur during initialization, as long as your initialization is purely assignments to variables, setting up the start state, the rest of the model checking is indistinguishable, right? Particularly because in Circus, their only state changes, they're not visible until while you're waiting for events. You can show this whole scheme is equivalent to starting in that state and moving from there. So we can switch this optimization on or off, but it's a very good reason for initializing your variables. If you do that, you've got a much better, a much quicker start. And this can save a lot of time in the model checker. It saves a lot of memory as well. The other thing, there are questions about the precise scope. It's described in the paper what we can translate. We can translate a lot of Circus, but not all of it. One of the questions that was raised was what can we do with Z schemas? How much Z schema translation can we do? So what we can do are schemas that look like this. This is just an init that just simply is assigning values to all the variables, direct, just written in Z style, and that can be translated into Circus assignments, and then that gets translated into gets and sets to the memory model. So the important thing to keep in mind with the memory model with gets and sets, ultimately everything we do with the state in our translation boils down to assignment statements, controlling assignment statements. So this is easy to translate. But somebody asked, couldn't we just translate arbitrary schemas? Well, if we did, I think I'd probably be giving an invited talk, because translating an arbitrary Z schema automatically into code, which is what's required, it's a challenging problem to automate. The principal approach, since this is Circus has refinement laws, and it includes the Z refinement laws, and there are tools for Z refinement, and in fact C refine, and various Circus tools can support this. The principled approach really is you've got some complicated schemas, do some Z refinement, and move them into the shape on the previous slide, and then we can apply our tool. It doesn't mean that we don't rule out, making our schema translator smarter in the future, but it wasn't initially a high priority. So to conclude kind of the kind of full paper, it's just a quite high-level overview of some of the design decisions behind the translator. So our baseline was the translation defined in the Compass deliverable. It takes Circus LaTeX format as input, right? It has now an extended ability to handle types, breaking up memory model, and at the end, a very pragmatic refinement. So thank you very much.